and go to current slide. Okay. Now this is where we left off last time. Again, I'll ask any questions, comments, issues, concerns, anything about either calculus or anything else. I will tell you this. Okay. Number one, I have seen several emails that have come in that have been sent to all students. So rather than copy them and put them on Blackboard and stuff, I thought, the students see these. I mean, they're going to the students. So I wanted to mention a couple of these. Whoops, here comes Jordan. So let me put him in. So I wanted to wait a little bit before I started on the calculus. And I marked. Recognize I admitted Brandon, but didn't put him on the roll. Now you're on the roll too, Brandon. And so is Jordan. Okay. A couple of the emails that come to mind from the last week or so, I think more recently than that. One was encouraging students to participate in tutoring. I think the Space Center has some great tutoring. I'm pretty certain that Dr. Thomas's STEM program has great tutoring. I think SSS does really good tutoring. So there's lots of things out there. Now, why am I telling you all this? You don't need the tutoring, do you? But I think you guys would be the very best tutors, especially for math and physics and some of the other technical stuff of anyone on campus. So I would encourage you to chase down those emails that were talking about tutoring and see if they need you as a volunteer tutor. I'm pretty sure they pay. I'm not sure how well it pays, but you set your hours. If you need a little extra cash and it's something that you would enjoy doing, please consider it. I'll tell you this. I learned math the best when I was trying to help somebody else learn it. When I was in the as an undergraduate, I was in the counseling system in the dorm system, and I liked tutoring anyway, so I was tutoring math all the time, calculus. I learned my calculus the most when I had to explain it to somebody else. I did okay in the classes. I did, well. I got good scores, but I really learned this stuff when I had to explain it to somebody. Go back through my notes and see, not just mechanically going through something, but why is this happening? So you'll really be doing yourself a service in addition to making a little money maybe if you consider tutoring. Now the other thing is, the three of you, are any of you planning to graduate this term, or are you going to be around for spring? Graduating? Oh, you'll be back. You'll be back. Okay. Watch your emails, because at some point, they used to say the term before you're planning to graduate is the best time to apply to graduate. I don't know in this new system if that allows that or not, but look at that email and see what it says about applying for graduation. There are a few little steps that have to be done in the right order. So even if you're not graduating this term, take a look at that so you'll be prepared next term, or whatever term it is that you'll be graduating. So all the paperwork gets done, everything gets done in order, all the T's are crossed and the I's dotted, and that you'll be able to get out of here with minimum anguish. Okay, so please take a look at that. All right, do you have any issues, concerns? I wanted to mention those two in particular because they are things that I had seen popping up on emails. I started to put them out there on Blackboard as announcements or whatever. I thought, wait, the students get this. There's no reason for me to copy them in there. But just go check your emails. Keep up with those. All right, if there's no issues, just a little bit of a review. What we started on Monday was looking in section chapter 5, integration, 5.6 Indeterminate Forms and L'Hopital's Rule. Here is a good example of an indeterminate form. Oh, here comes Ashton. I was hoping he'd be here. We got perfect attendance again today, folks. Way to go again. Okay, this is 2 days in a row, all week. Perfect attendance. Yesterday in my linear algebra class, perfect attendance. Last Monday in differential equations, perfect attendance. So way to go, folks. Keep it up. Get the most bang for your bucks here. Be here every chance you can. All right. So what we were talking about, or I was talking about anyway, was indeterminate forms. And this is a classic example of one. The numerator here, what we have is a limit. If I can get my pen to show up somewhere. There it is. The limit as x approaches 0 of this expression here. Whereas x is going to 0, 2x of course is going to 0. E to the 0 of course is going to 1. 1 minus 1 is going to 0. Now that's not bad on its own. The fact that the denominator is also going to 0, that is a classic example of a 0 over 0 indeterminate form. Remember, if that would have been 17 over 0, hang it up, no limit exists. That is undefined, can't do it. In the old days, we used to say anything you had a 0 in the denominator was undefined. That was back before we knew any better. Now that we're into calculus and into limits, we know that if you've got a 0 over 0, this form right here, if I can get my pen to show up again, there it is. That form right there, 0 over 0, that may be undefined or it may have a limit. This is a classic example of a 0 over 0. We can't tell. L'Hopital's rule tells us that we can then take this and do the limit as x approaches 0 and take the derivative of both of those. What's the derivative of e to the 2x? Anybody? Is that it? Chain rule? The derivative of e to the 2x is e to the 2x. The chain rule, then you take the derivative of the innermost part, and that's derivative of 2x is 2. Derivative of minus 1, 0. Okay? The derivative of x, please tell me you can do that one. One, excellent, okay. Now let's take the limit of this. As x is going to 0, 2x is going to 0, e to the 0 is going to 1, 2 times 1 is 2, 2 over 1 is 2. There is the limit. Believe it or not, the limit of e to the 2x minus 1 over x is going to 2. Okay, who would have thunk? Okay, no real indication that was going to be showing up, but that's exactly what the book got. Now, by the way, a little before we got there, I guess I should have mentioned this. In your left margin on page, and I guess I said part of this one, not all of it, we're on page 347, example 1, top of the page there. Just to the left of that, there was an exploration given. It says numerical and graphical approaches, and it gives several examples there, and it's something very similar to what, well, not exactly like we did, but it's I was trying to think, it's one of my classes we were doing exponentials and but not of base e, and those were those. Do you feel like that would be something beneficial to go over those 4 real quickly? They're not in the slide set, but I'll be glad to do them if you think they would be beneficial. Anybody? If you got your books open, ebooks or whatever, page 347, the exploration just to the left of example 1. While y'all are deciding that, I'm going to go on and show you how the book did this. The direct substitution results in the indeterminate form 0 over 0, just like we did, because the limit as x approaches to 0 here is 2 times 0 is 0, e to the 0 is 1, 1 minus 1 is 0. And of course, as x approaches 0, that's going to 0. Okay, x is going to 0. That's pretty obvious. Okay, but you can apply L'Hopital's rule, okay, and you take the derivative of the numerator and the derivative of the denominator and take the same limit that you were doing before, and that gives you 2x e to the 2x over 1. Take the limit of that. As x goes to 0, 2x goes to 0. E to the 0 goes to 1. 2 times 1 is 2 over 1 is 2. Okay. Now, before we go to this, what did y'all think? Do you want to do that exploration? I think it's something you could probably do on your own, but I'll let you decide. Do you want to do that? Somebody speak. I know I let Ashton in, but I don't see him. Did he ever make it in? I just noticed that he wasn't showing up on the side. Not everybody shows up on the side, but he's not here. So, have any of you been in communication with Ashton? Okay, if you have a way to get in touch with him, ask him if he's having problems, because I clicked the button to let him in, but I just assumed he got here, but I never saw him after that. So what do you think? Exploration, do it or not? Anybody? Y'all are, you're good? Okay, what does that mean? You want to do it or you don't want to do it? Don't. Okay. All right, I'm all in favor. All right, then after example 1, here's another form of L'Hopital's rule. States that if the limit of f of x over g of x approaches, whoops, I'm on the wrong pad, approaches infinity or negative infinity, this is a strange way to state. If the limit of that as x approaches infinity or negative infinity produces an indeterminate form either 0 over 0 or infinity over infinity, then you can still do the same thing. You can take the limit. See, before we were letting limit x go to 1 or 0 or something else. This time, if x is going to infinity and that ratio of two functions, or you can then go, if that's either going to be indeterminate 0 over 0 or infinity over infinity, again apply L'Hopital's rule and see if that simplifies the issue. Sometimes it may, sometimes it may not. You know, you may have to do it several times. Or at some point you find out, nope, it's exploding, it's going to infinity, you're not going to find a limit. Because it says, provided the limit on the right exists. Okay? So let's do, well, it won't advance now. I guess when I use the keypad, the pad, it cuts off so it won't advance until I click on something else again. So here's example 2. Here's a limit as x approaches infinity of, if I can find my pen, where is it? There it is. Okay. Log x, as x goes to infinity, keeps getting larger and larger and larger and larger. X also keeps getting larger and larger and larger. So this would be a classic example of an infinity over an infinity. So let's apply L'Hopital's rule. That would be the same as the limit as x is still going to infinity of, what's the derivative of 1 over x? I'm sorry, I gave it away. What's the derivative of log x? Anybody? No, derivative of log x is 1 over x. The derivative of x is 1. That denominator would be 1. Derivative of x would be 1. Derivative of log x is 1 over x. So this is the same as the limit. I'm doing this out in gory detail this time. Usually I don't. Of 1 over x. And as x goes to infinity, x getting very, 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 very large, 1 over a very, 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 very large number is going to 0. Right? So that limit does exist, and it is 0. Now, part of what the exploration was talking about, in some sense, I wasn't going to do it anyway, was looking at it graphically. And if you picture log x, remember, goes up really slowly, whereas 1 over x goes up much faster, okay, especially for large x's. So after a while, the denominator is quite a bit larger than the numerator. Sure, that's going to 0. Okay, let's see how the book did it, or the slideshow did it. Because direct substitution results in indeterminate form, infinity over infinity, which we did here, you can apply L'Hopital's rule to obtain derivative of log x over derivative of x. Whoops, wow, look at that. Derivative of log x is 1 over x, derivative of x is 1, so that just gives you 1 over x. And when you take the limit as x gets increasingly large, numerator stays the same, denominator gets bigger and bigger and bigger, that's obviously going to 0. Okay, so that limit does exist, and it's equal to 0. That ratio will never be equal to 0, but the limit will be. Does that make sense? Any questions? All right. That was it for page 347. They're skipping example 3. So let me go back one slide and let's go to the whiteboard. Oh, wait, here was Ashton, I think, coming back. I couldn't see for sure, but he's the only one we're missing. Yeah, there he is. Okay, Ashton, I tried to let you in before. Did you get in but couldn't connect? Well, I'm glad you're here anyway. Okay. All right. So let's go to the whiteboard. Just as I was clicking on that, I thought I saw your name pop up, but you got buried behind all the paraphernalia that's on the board here. So I'm going to, while y'all are sitting there waiting, I've got to move this toolbar out of the way, taskbar, whatever you call it, and I've got to scoot the whiteboard. Even though all you see is white, I've got limited room to write, but I've got a bigger screen so I can scoot it to the left and up as much as I can to give me maximum white space. So here's example 3, top of page 348. And this is one, unlike the other two, they gave you simple ones from the PowerPoints, and then for the more difficult one, or another level of difficulty or effort you have to make, they left that one off, which is sort of typical. Here's the limit we're looking for. The limit as x is going to negative infinity. We don't usually do that, but it's doing it. It's fine. Of x squared over e to the minus x. Okay. Now, you first, as always, see what just plugging it in does for you. Well, certainly the numerator, if x is going to negative infinity, and you're going to square that number, what that means is a very, 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 very large negative number. You square a very, very, very large negative number, and you get an even larger positive number, because negative times negative is positive, and a large number multiplied by itself gets increasingly big. So that's going to infinity. And that's what we used to write before, so I'm going to put it, if I can get the pen to, there it is. So this is going to positive infinity. Okay, now what's happening down here? It's e to the minus a minus, so that's going to be a positive infinity. E to an infinitely large positive number is really going to infinity fast, so sure enough, this is e to the, this one's also going to infinity. So you have the classic case, infinity over infinity. But L'Hopital's rule applies, so let's try it. This will be the same as the limit. Yuck! Same as the limit as x approaches negative infinity, that doesn't change, of, and I'll take the derivative of the numerator. What's the derivative of x squared? Anybody? Come on. 2x, perfect. Okay? And what's the derivative of e to the minus x? Derivative of e to the minus x is e to the minus x. In chain rule, you take the derivative of the innermost function. Derivative of minus x is just minus 1. So that's why you have a minus sign here. All right, now let's do it again. What happens if x is getting very big negatively? So x is going to be a very large negative number. You double that and it gets even a larger negative number. So this time it's going to negative infinity. Okay, the numerator is. How about the denominator? Was x is going to a very large negative number, minus x is going to a very large positive number. So that's going to infinity, but then you're negating that, so this is also going to negative infinity. We're no better off than we were here. In fact, it looks a little worse because now they're both negative. But it's still, L'Hopital's rule still applies. So let's try it again. Let's take the limit as x approaches negative infinity. Don't change that. Okay. Now let's take the root of 2x. What does that give us? 2. Excellent. Okay. And the denominator, take the derivative of minus e to the minus x. Isn't that e to the minus x? Because the derivative of e to the minus x is e to the minus x. Then you take the derivative of the innermost part is a minus 1 there, but then you have a minus here. Minus times minus is plus. Now let's take, well, the limit of 2 is 2. Okay, I can do that one. The limit as x goes to negative infinity, the negative x goes to positive infinity, e to positive infinity goes to infinity. And 2 over a very large number is going to 0. So that limit is indeed 0. How did the book do? Oh, good for them. I was looking at the wrong problem. They got it right. I was looking at the wrong one. I said, where'd they get a square root in there? But they didn't. That was example 4. I was looking at the wrong part of the page. It's also, this limit is 0. Any questions on that? Does that make sense? Do all parts of that, anything that you need, have a question about? Okay, then, well, I'll leave it up there for a little bit. Let's go back to the slideshow. Okay, 5.6. I guess that other one's 5.7. Okay, we'll go from current slide, which if I can get it to land on it. Okay, that was example 2. We just did example 3. Now we do the wording after example 3. In addition to the forms of infinity over infinity, and I'm sorry, 0 over 0 and infinity over infinity, there are other indeterminate forms such as 0 times infinity. Ooh, who wins that one? Certainly, most of the time, 0 times a number is going to be 0, but this is an incredibly large number. Is it going to overpower the 0? You would think not, but who knows? Or how about 1 raised to the infinity? Well, man, that seems like that ought to be 1 because 1 raised to any power is 1. So, but how about infinity raised to the 0th power? Anything else to the 0th power would be 1, except 0 to the 0 is undefined, but infinity to the 0, that's not even a number. Seems like that should be 1. Oh, and here's that one I just said. What do we mean by 0 raised to the 0th power? Before this we said undefined. Is it still undefined? Before we said 0 over 0 was undefined, but no, that's indeterminate. So these are also indeterminate forms. And here's another one. How about infinity minus infinity? Which infinity is bigger? Who wins that battle? Okay. So what was it? So for example, consider the function, the first of those 4 limits, okay, 0 times infinity. Okay. Consider the following 4 limits that lead to this indeterminate form. So here's what we got. The limit as x goes to infinity of, I don't know why they wrote it this way, but x over x. Okay. That's 1 over x times x is the same as x over x. X going to 0, x going to 0. Okay. Well, if you think about that, this is 0, 1 over 0, which is infinity, times 0. That's this form right here. But guess what? X over x is 1. So you don't have to do L'Hopital's rule. You don't have to do anything. That limit is 1. Wow, didn't see that coming. I thought it was either going to be 0 or something else. Turned out being 1. How about this one? The limit as x goes to 0 of 2 over x times x, or 2x over x. You don't need L'Hopital's rule. That's the limit's going to 2. The function's not equal to, well, actually this one it is. X can't equal 0, but the limit of the function is 1 in this case, 2 in this case. Okay, now how about this one? 1 over e to the x, that's a 0. No, I'm sorry. Yeah, that's a 0 because limit going to infinity. X, as x goes to infinity, would be going to infinity. What does this one do? Well, this you do have to have L'Hopital's rule. Use L'Hopital's rule. Because this is going to infinity, that's going to infinity. Derivative of this is 1. Derivative of this is e to the x. 1 over infinity is 0. Okay? And then how about this one? This is e to the x over x, the reverse of this one. And you just do the reverse again. The derivative of e to the x is e to the x. Derivative of x is 1. The limit as x goes to infinity of e to the x. Man, that's taken off and going to infinity very rapidly. Okay? So, there are 4 different limits leading to 4, and they're both of the form 0 times infinity. They're all going to different limits. 1, 2, 0, and no limit, infinity. Okay. These 2 you didn't need L'Hopital's rule at all. You just work them out algebraically. These 2 you would need L'Hopital's rule, and those show you what the limits are. So you just rewrite it so it does fit L'Hopital's rule. All right. Because each limit is different, it is clear that the form 0 times infinity is indeterminate in the sense that it does not determine the value or even the existence of the limit. Basically, you attempt to convert each of those forms that we're talking about into a form that you can apply L'Hopital's rule for. So why name those others indeterminate forms? Just say, work to see if you can get it in one of these basic forms. That's what you're doing. Seems like they're going out of their way to make it a little more difficult when it wasn't necessary. So here comes example 4. Evaluate this limit. Okay? Now, I think what I would do first is rewrite this. okay? And I would rewrite, oh, well, let's just evaluate it first. As x is going to infinity, e to the minus x, okay, e to the minus 1 over e to the infinite number. Well, I'm doing what I'm going to do in a minute. That's going to get infinitely small, going to 0, but this is going infinitely large, okay? So, but don't worry with that. Do it this way. Write that as a limit as x goes to infinity of square root of x is the square root of x. Okay, in fact, I want to write it as x to the 1/2. I'll do that in a minute. And put this in the denominator, over e to the x. When you put it in the denominator, you lose the minus sign. Now that's one of our forms. This is going to infinity. This is going to infinity. So now we'd use L'Hopital's rule, but like I said, rewrite this as x to the 1/2. Okay? And do L'Hopital's rule, and that would be limit as x goes to infinity, don't change that, of, what's the root of e of x to the 1/2? Be 1/2 x to the minus 1/2, right? Yay? And this one is just e to the x. All right, now let's rewrite that as 1, that's the limit, as x goes to infinity, of 1 is in the numerator here. This 2 comes down to the denominator. This square root of x comes down to the denominator because it's the minus 1/2 power. And this is already in the denominator, e to the x. Well, guess what, folks? E to the x is going to infinity, square root of x is going to infinity, and 2 doubles it, okay? This obviously has a limit of 0, okay? I have nothing else that e to the x is going to overpower everything in the denominator. Let's see how they got it right in the book too. Good for them. Let's see how they did it. If they did it the same way. Any questions before we move to see what they said? All right, because direct substitution produces an indeterminate form, malarkey. Try to write it in this form, infinity over infinity. That's what you do. I mean, I don't worry about that being something else. In this case, you can rewrite the limit to fit the second form, and this is limit, which is what we did, of square root of x over e to the x. That's exactly what we did here. Okay? Now, that is an infinity over infinity, which leads to L'Hopital's rule. And they did it with the radicals. I sure don't like doing it with the radicals. Excuse me just a second. I grabbed me a little snack right before class, but I didn't get enough to drink. So let me... My throat's getting dry. Maybe that will help. Okay. I sure don't like taking derivatives that way. I change it to x to the 1/2, and that makes it much easier, but that's the correct answer. And when you put everything in the denominator, it's all in the denominator. 1's the only thing left in the numerator, and then you have 2 times square root of x times e to the x. They're all, 2's not that big a number, but as x goes to infinity, square root of x is, and e to x certainly is, so that's got to be going to 0. If your denominator is getting big, numerator is fixed, that's going to 0. Any questions? All right. Now, trying to find, okay. They skip a little bit of verbiage at the top of page 349. Now, I don't know if y'all can see your books at the same time you're watching the Zoom. I know that some people only have ebooks, and that's almost impossible to do. They do a little thing here. I think that we've hit it okay, but just in case you feel like we haven't, I'm going to hold this up so you can see what they're talking about here. This is their explanation here. I don't know if I can get it close enough for you to read, but far enough back so you can see the whole line. It's going to be hard to do. It gets too blurry, okay? Basically what they're saying here, when rewriting a limit into one of the forms 0 over 0 or infinity over infinity does not seem to work, try the other form. Now, they don't really say. For instance, in example 4, you could have tried to write that e to the one that we just did. Let's go back to that. If they had written that as e to the minus x on top and square root of x, or square root of the negative square root of x, e to the minus 1/2 on the bottom, that would have been a really lousy choice. That yields an indeterminate form 0 over 0, and it just makes everything really awkward. So if you can, keep it simple. Used to be a phrase that went after that, but I won't say that one. But try to keep it as simple as you can. If simple doesn't work, then get more complicated. But don't start off being complicated and then lose all your meaning. Okay? So then it picks up this. The indeterminate forms 1 to the infinity, 0 to infinity to 0th, or 0 to the 0 arise from limits of functions that have variable bases and variable exponents. Okay? Now, what do we do with those? Here's this example. And this is one we actually saw before, I think. Okay? And you were supposed to kind of just remember it. But let's see how we proceed with this. Okay. This is what you're asked to evaluate. Now, what you've got here, 1 plus 1 over a very big number. So this itself is going to 0. The 1 then would just be going to 1, okay, because 1 plus 0 would be 0. But 1 raised to an infinitely large power, that would be this form right here. Now, how do you handle that? Okay, here's what their suggestion is, and this is what you typically do. Okay, whenever you have exponents involved, think in terms of taking a log, because a log undoes an exponent. So here's what we're going to do. We're going to set this equal to y. Why not? That's what we're looking for. We're going to try to find out what y is. Now, once you do that, that then enables you to take a log of both sides. So this gives you the log of y is equal to. Now, can you take a log inside a limit? I don't know if you remember it, but yeah, you can. So this would be the limit as x goes to infinity. And when you take the log of this, that by the rule of logarithms is x times 1 plus 1 over x. Okay? That's one of your rules of logarithms. I'm sorry, I left off my log, didn't I? The log, I can't write, the log of that. Because you took the log of this, and that's x times, okay, I got this all screwed up. I can't erase here. This is x times the log of this. Okay, so let's pause a moment here and see if we can evaluate that one. This would be, this is going to infinity. This is going to 0. 1 plus 0 is 1. Log of 1 is 0. So now we have a form 0 times, infinity times 0, which is one we talked about before, wasn't it? Yeah, infinity times 0, right there. Yeah, well, yeah, there it is. So we still have an indeterminate form. Okay. So what do we, let me make sure I'm doing it the same way they did. Yeah. Now they use a little trick. And here's the trick. This is still log y, remember that? Here's the trick they use now. That's the limit as x goes to infinity. See, remember when I said we had a form that was infinity times 0? See if you can get it into a 1 over form. So what that is x here is the same as 1 over a 1 over x. Does that make sense? Okay. And then up here you just have your log of 1 plus 1 over x. Now you might think, wait a minute, what did that do for us? But that's indeed what they're doing next. Okay? The log of 1, yeah, make sure I got it right. Now, because you see, basically this is what it's saying. X can be written as 1 over 1 over x. To verify that, this is the same as 1 divided by 1 over x. And how do you divide a fractional form? You keep the first one, multiply by, I shouldn't use a times, multiply by x over 1. And that sure enough is x. So yeah, that's right. Okay. Now let's take the limit here. This limit as x goes to infinity, this is going to 0. 1 plus 0 is 1. Log of 1 is 0. So that's going to 0. Now this one, as x goes to infinity, x is getting infinitely large. 1 over x is going to 0. Ho! That is a L'Hopital form. So let's take the derivatives of numerator and denominator. That's no walk in the park either. But that's going to be the limit as x goes to infinity. Okay, and what is the derivative of a log of this thing? Now I'm going to rewrite this thing to be x plus 1 over x. Are you okay with that? 1 is the same as x over x, so x over x plus 1 over x is the same as x plus 1 over x. Okay, so what's the derivative of log of x plus 1 over x? Well, that's going to be its reciprocal, which is going to be x over x plus 1. Then times the derivative of the inside. Yuck, that is a quotient rule. Okay, and the quotient rule would be low, that's x, d high, derivative of the numerator is 1, that's not bad, plus high, x plus 1, d low, well, that's 1, over low, x squared. Okay? Ooh, that's what your numerator became. The denominator simply becomes, think of this as a x to the minus 1. Derivative of that would be a minus x to the minus 2. Ooh, don't know what that was. Let me see. Are y'all, we don't have anyone that had to get kicked out and come back in. Okay. All right. I guess the computer's just making noise. Could be y'all are chatting or something, that's fine too, but I just want to make sure no one got bumped out of the class, the internet failed or whatever, and you're trying to get back in and I'm not recognizing that, so that's why I always check. Now that's a real mess so let's see if we can make anything. Now remember, this is log y. I keep saying that. it is important to remember this as log y, okay, is equal to the limit as x is approaching infinity. We're not changing that any. Now let's see if we can straighten out this mess any. Number one, I'm going to pull that minus sign out front. So it's going to go there. Now, a 1 over x squared, no, 1 over 1 over x squared is going to be x squared. So that's going to move up top. Okay, I may not want it there, but I'm going to move it there for now. X squared, and that will basically cancel out this x squared. So let me just go on and wipe those out so I don't have to deal with them anymore. Okay, so those have gone away. Okay, now what's left? You have an x squared. No, let's go and work this out. X plus x is 2x plus 1 times x would be a 2x squared plus x. That's in the numerator. And then the denominator you have, why did I do that? Okay, well, maybe I had to. X plus 1. Okay. Now that form is still an infinity over infinity, actually a negative of that. So we could do L'Hopital's rule again, and that would be the limit as x goes to infinity of 4x plus 1 over yeah, 4x plus 1 over 1, and that looks like to me it's going to infinity. And if log y is going to infinity, pretty good indication that y would be going to infinity too. I think I've done something wrong here. I think in some of my gyrations there, I messed something up. And it's right in here. I don't know how I messed that up. Where I was getting all these x's in here, they were getting 1s. And that's disturbing. How did I screw that up? It may be when I went to this form here. That is right. The log of that would be the inverse of that times the log of, the derivative of this, which would be x I think I do see someplace I hit it. X times the derivative of the numerator is just going to be x, and I think I got that right, plus x plus 1, the numerator, times the, oh, that's a minus. That's where I messed it up. That's a minus. Quotient rule, low d high minus high d low. And therefore the x's go out here, and that leaves you a 1 over x squared. Okay? So yeah, that's where I messed it up. Sorry about that. So rather, I can't erase on this board. So what I'm going to do is just show you how they did it, and we'll work through there. Sorry about that, because that's minus sign, always trips you up. Because direct substitution gives you indeterminate form 1 raised to the infinity. We don't know what that is. To begin, assume that the limit exists and is equal to y. So that's what we did here. That's the same thing we did. There it is, y is equal to that. And then we take the log of both sides so we can deal with that exponent here, a variable exponent. Do that. So we did. Log of y is equal to the limit, now the log of this thing. But the log can move inside the limit, so that's what they did a different step here. I did it all at once. They did a separate. Log of y is a limit as x goes to infinity of this thing. Now at this point we could pick up and go again. Okay? Now that's still an indeterminate form. That's an infinity, and this is times 0. Okay? Now I'll let them do the next trick because the same thing we did. We rewrite this as the log of this thing here. That's just rewritten in the numerator. And we move this x to be a 1 over x in the denominator. And I showed you why that's true. Okay? Now, this is a form as x goes to infinity. This is going to 0. 1 plus 0 is 1. Log of 1 is 0. And this is going to 0. So now you have the classic L'Hopital form, 0 over 0, indeterminate form of that. So what we do is take derivatives. And this is where I messed up before. So let's see if I can rectify myself here. We're going to take the derivative. So this will be the limit as x goes to infinity of, now, and again, now I'm going to do the same thing I did before. I'm going to rewrite this as x plus 1 over x. That's what your argument is here. Least common denominator is x, so x over x plus 1 over x is x plus 1 over x. So take the derivative of that, the log of that, and that will be the reciprocal of that, x over x plus 1, times derivative of the inside. And that would be low d high, low is x, derivative of the numerator is 1, minus high d low, x plus 1, times derivative of the denominator is 1, over x squared. And your denominator, derivative of that is minus 1 over x squared. Okay, now, as I said before, these can go out. I did them a little. Now let's bring the minus sign out front. So that's going to be, I'm going to bring it all the way out front, minus the limit as x approaches infinity of, now, this becomes x minus x is 0, and this becomes a minus 1 here. So that minus 1 wipes that one out. Okay? And what we have then is just what we have left over here is x over x plus 1. Okay? Now, that's infinity over infinity. Do L'Hopital's rule one more time. That's the limit as x goes to infinity of 1 over 1, which is 1. Well, that limit obviously is 1. The derivative of this is 1, derivative of that is 1. But remember, this is log y. So log y is equal to 1. E both sides. And that gives you y is equal to e. And that is indeed what way back we said this is what e is. Remember that last time? We just gave that off the top. Now we've shown indeed it is. Okay? Here's them going through those same patterns. They do it slightly differently than I did. They left this in this form, which is kind of awkward, but they did, and it worked okay. And when they get to this form, that gives them 1 over 1 is 1, and log y is 1. Same thing we did. You can conclude that y has to be equal to e. So this gave you exactly what we used before. That is the definition of the number e. And we did a few of those. No, maybe that was my last class, my next class, when we were doing infinite series. Sorry, that wasn't you guys. That was my other class, Cal 3 class. Okay. Sorry, I was thinking it was you. It wasn't. Okay. You can use a graphing utility to confirm that result, and there you have it. This is going as x gets larger and larger and larger. This is approaching 2.71 blah 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 blah. Something a little bit greater than 2. In fact, it's going to be close to 3. It keeps going up ever so slightly, and it takes a while to get there. Never gets there, but it gets closer and closer to that. All right. Any questions? That was, sorry about dropping a minus sign or failing to put one in. L'Hopital's rule. Let's see. Okay. Only, sorry, like I said, I was on a Zoom call. At 9 this morning, so I didn't have as much time to get ready. So I'm dehydrated, sorry. L'Hopital's rule can also be applied, and let's see, where are we now? That was example 5, bottom of page 349. Yeah, to one-sided limits. This is the top of 350. L'Hopital's rule can also be applied to one-sided limits as demonstrated in examples 6 and 7. So here we're going to do example 6. Let's evaluate this one. Now this time x is going to 0 only from the positive side, okay? And what we're looking at is sine of x raised to the x power. Whoa, what in the world is that? Sine of x as x approaches 0 is of course approaching 0, okay? But x is approaching 0, so you got 0 to the 0th power. What in the world does that mean anyway, okay? So again, we're going to use the same little trick we did before. Anytime you have a variable exponent, write that as a function, y, and then take the log of both sides. So that would give you log of y is equal to, and I'm not going to mess with this, I'm going to pull this all the way on the outside, the limit as x approaches 0 from the positive side of, now the log of sine x to the x is the same as x times the log, not limit, log of sine x. Okay, that's rules of logarithm and the fact that you can take the log inside the limit sign. Okay, well, what kind of form do we have now? This is 0 and this is log sine x as x goes to 0. This is 0, but you can't do the log of 0. So here we have an indeterminate form that would be 0 times the a negative infinity. All right, so let's try the same trick we did before and do the limit as x goes to 0 from the positive side only. See, if it was going to the negative side, that won't work at all. You cannot take the log of a negative number, period. You can't take the log of 0 either, but when you know where it's going negative. Log of a negative number, not even close to being defined. Okay? So what we're going to do is similar to before. In the numerator we have the log of sine x. This is not writing very well. Over 1 over x. We took the x and put 1 over x. All right, now let's take a look at this. This is going to infinity, okay, and actually negative infinity. This is going to positive infinity. So we have an infinity over infinity. So can we do it again? Can we take L'Hopital's rule again? Well, we haven't done L'Hopital's rule yet. Now we can. Limit as x is going to 0 from the positive side. Derivative of that would be 1 over sine x times cosine x. So that would be cosine x over sine x over minus 1 over x squared. Okay, that's kind of a mess. So let's bring that back upstairs and bring the minus sign out front and make it the limit as x approaches 0 from the positive side of x squared cosine x over sine x. Okay. Feel like we're running in circles? It kind of does, doesn't it? Because this numerator is 0 times 1. Now that's not indeterminate, that's 0, okay? The denominator is 0. So again, you have a 0 over 0 situation. So let's try it again. So that would be minus the limit, and we may be running in circles here, let's just see, as x goes to 0 from the positive side. This is a product rule. So let's do 2x times cosine x plus x squared, make that a minus x squared sine x. Okay, over sine x. This seems to be getting worse and worse and worse. Let's give them a shot here. I don't want to take up too much class time. Because direct substitution produces an indeterminate form, we rewrite that same way it was written before, and then we take the log of both sides just like we did before. They take the log on the outside, then they bring the log on the inside, and just like we did, and then it gives you x sine log sine x. Okay, that's log y, remember that. Okay, that's still an indeterminate form, so that same trick we did before, log of sine x over 1 over x, so we're doing it the same as before. And they wrote this as cotangent x. I was thinking of doing that, but I was afraid that would just clog the issue. Maybe it'll make it clearer, okay? But that is correct now. That's still, and what they did was flip it over then, bring the minus x squared up top, and 1 over cotangent is tangent. It's still a 0 over 0 form, which is what we had. Do L'Hopital's rule again, and this gives you a minus 2x over secant squared x, which is what I was afraid of. And as x goes to 0, this is going to 0, but this one's going to 1. So maybe it would have been better to pursue it this way. Secant squared x, as x goes to 0, is going to 1. So you have a 0 over 1, which is indeed a 0. So sure enough, that is a limit of 0. I think we could have gotten there my way, but it was just really ugly. Okay, so anyway, that gives you your limit of 0. Let's see now, because I forgot, that was log y is 0. You can conclude that take it e of both sides, you get y is equal to e to the 0, which is 1. So therefore the limit that we first started with is actually 1, not 0. Okay. Now here's another one. Let's take a look at this one. Not batting too good today, am I? All right, there's no rule for, well, let's see. This will be the limit as x approaches 1 from the positive side. Now, let's just plug in and see what we get. Log of 1 is 0. So you have a infinite minus, and 1 minus 0 is also 0. So you have a infinity minus infinity. All right, that's not very pleasing. So what would we do? Well, one thing it looks like we've got to do is get it over least common denominator. I don't know if that's the direction they're going to go. Let me see. This is example 7. Yeah, I believe that is it. Okay, so let's do it to it. Okay, now the least common denominator of that is going to be log x times x minus 1. So that's going to be an x minus 1 here minus a log x here over log x times x minus 1. Now check me on that and make sure that's correct. I believe that is. Yeah. All right. Now that doesn't look very promising, does it? Well, let's see what happens. It should still come up being something bizarre. This will be 1 minus 1 is 0 minus 0, that's a 0 in this case, over 0 times 0 is 0. So at least we have a L'Hopital's rule form, 0 over 0, not an infinity minus infinity. So we've made the first step. I think that's the correct step. So now we do the derivative, and that would be the limit as x approaches 1 from the positive side. And by the way, why does it have to approach it from the positive side? Because we want this to stay positive. We want this to stay positive, okay? Not real clear now why we do, but it appears to be the case. So let's see what we have. If we take the derivative of the numerator, you get 1 minus 1 over x over, here's a product rule. So it's the first log x times 1, derivative of the second, plus second x plus x minus 1. There, I started to do it again. X minus 1 over x. That's the second time derivative of the first. Okay. Now that form is kind of ugly. Okay. So what I'm going to do here, and it may not be good, but I'm going to do it anyway. Okay. Is multiply everything in numerator and denominator by x. Okay, so that would be multiplying the numerator by x and the denominator by x. X over x is 1. That's fine, no sweat there. So that gives me an x minus 1 over x log x. I can't write log x well. X log x plus x minus 1. Okay, let's see what that gives us. As x goes to 1, numerator is still going to 0. The denominator is still going to 0. Okay, so let's do L'Hopital's rule again. This is getting tiring, isn't it? I'm going to come over here and do it. And that will be the limit as x approaches 1 from the positive side. And that derivative is just going to be 1. Finally. This derivative in the denominator is going to be, again, a product rule. So that's going to be x over x. That's the first time derivative of the second. plus the second times the root of the first, log x plus 1. Okay, let's see what happens there if we take the limit there. Numerator's got to be 1. This is going to be 1. This is 1 plus 1 is 2. As x goes to 1, this goes to 0. So it looks like we wind up with a 1/2. Oh, could it be? Yes, it is. That's exactly what we get. Okay. Let's see how they do it. Unfortunately, my writing's going to be in the way, but hopefully you can read theirs over mine. Oh, no, they're going to put a lot of words in there. Because direct substitution yields an indeterminate form, which is blah, 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 you should try to rewrite the expression to produce the form which you can apply L'Hopital's rule. In that case, combine the two fractions, least common denominators, just like we did, to get x minus 1 minus log x over log x times x minus 1. They just did it in the opposite form. Okay, now, if you get that form, which we're going to go to the next page on, because direct substitution there produces an indeterminate form, 1 minus 1 is 0 minus 0 is 0 over 0 times 0. Yeah, that's indeterminate. Now take a derivative of both of those. And derivative of the numerator is 1 minus 1 over x. Okay, derivative of log x is 1 over x. Derivative of the denominator is the first times the root of the second plus the second times the root of the first, which is just log x. All right. Now that's messy in its own right. I think they're going to skip a bunch of steps here. Yes, they are. Okay. And let me show you what they skipped. They wrote that numerator as x minus 1 over x, just like we had done before. Okay. The denominator they wrote as x minus 1 plus x log x over x, and then canceled out the x's. Okay, so now take the limit of this as x goes to 1. That's still a 0. This is still a 0. And this is 1 times 0. That's still a 0. So another L'Hopital's rule. Okay, I hope they wrote it all down. Now we get a 1 finally here. And here we get a 1. That goes to 0, and then you get x over x, which is what this is, plus log x. Take the limit of that as x over. This is 1, this is 1, and this is log of 1, which is 0. So 1 over 1 plus 1 is 2. Sure enough, we got our 1/2. Wow. Lots of L'Hopital rules in those. Okay. Now, they said you can check the reasonableness of this using a table. I don't know that this is anything, but you're approaching 1 from the positive side, and if you put in a 2 here, you get this number. Put in a 1.5, which is closer to 1, and you get this number. 1.1, even closer to 1. 1.01, even closer. 1.001 here. 1.0001, you can't see that. That gives you there. And by that time, you got really close to 1/2. To 6 decimal places or something like that, you're at 0.5. Okay. Now, that was example 7. Here is the comment on the bottom part of page 351. The form 0 over 0 and infinity over infinity, those are indeterminate forms that we can use L'Hopital's rule on. The others we have to adjust to get it. The infinity minus infinity, 0 times infinity, 0 raised to the 0th, 1 raised to the infinity, 0 raised to infinity raised to 0. They have been identified as indeterminate. There are similar forms you should recognize as determinate. In other words, if you have an infinity plus infinity, guess what? That's not going anywhere but huge. Okay? Minus infinity minus infinity. That's going huge negatively. 0 raised to the infinity power, which I thought they listed that before, that is still going to be 0. And 0 raised to the negative infinity, that's basically 1 over 0. That's getting infinitely large. Those are not indeterminate forms. I thought they had this one listed as one earlier. Let me go back and see. I thought for sure they listed that. Taking class time to do this. No, I must have skipped over. Oh, no, here it is. No, they didn't. They did infinity to the 0. They didn't do 0 to the infinity. Okay. I falsely accused them. Sorry. It'll get, yeah. This is not an indeterminate form. That's 0. 0 raised to any power is 0. Okay. Well, except a negative infinity. That means a 1 over 0. That's going to positive infinity. Okay. As a final comment, remember that L'Hopital's rule can be applied only when you can get it into a form of 0 over 0 or infinity over infinity. Those other indeterminate forms, you don't apply L'Hopital's rule. You adjust them until you get them into one of these two forms. For instance, the application of L'Hopital's rule here is not correct because as x goes to 0, e to the 0 is 1, and this is 0. 1 over 0, that is not an indeterminate form. That doesn't exist. Does not exist. Do not do L'Hopital's rule on that because you don't fit the criterion. It's either 0 over 0 or infinity over infinity. That was a 1 over infinity, a 1 over 0. That has no limit. The reason this application is incorrect is that even though the limit of the denominator is 0, the limit of the numerator is 1, that doesn't meet the hypotheses that the given condition for L'Hopital's rule. So you can't use it. And I think that's the last slide in the section. All right, finally. Okay, so here are your homework exercises in example 6. The concept checks are always listed here. I usually ignore them because there's nothing really for you to do, but I think you shouldn't ignore them. You should take a look at that, think through what they're asking you to think through there. Okay? But homework exercises are due either 3 or 5. They're both at Calc Chat. Any of the odds 7 through 13, they are all at Calc Chat. 7's at Calc View. Any of the odds 15 to 41, they're all at Calc Chat. 29's at Calc View. Any of the odds 43 to 61, they're all at Calc Chat. 51's at Calc View. 63 or 65, you can explore doing those if you're interested. They should be at Calc Chat. 67 should be at Calc Chat. Any of the odds 69 to 73 should be at Calc Chat. 75 or 77 should be at Calc Chat. And you can think about doing 79 or 82. That's sort of like the thing they just showed us, something that was done incorrectly. You figure out why it was done incorrectly. I sort of hate for the book to do that, to show you something and say, oh, but this isn't correct, but you figure out why. They put big red X's there to indicate this is not correct. I just hate for the book to print things that aren't. 83 should be at Calc Chat. 85 should be at Calc Chat. And then any of the odds, either 87 or 89 should be at Calc Chat. 91 or 93 should be at Calc Chat. 95 through 99 should be at Calc Chat. Those are true false. 101 should be at Calc Chat. Excuse me. 103 should be at Calc Chat. And then any of the odds 105 through 109 should be at Calc Chat. There is a further information given here. If you're interested in that, you might want to go think of that as a paper topic. but then 111 is a proof. Any of the odds, 111 through 115. If you want to try any of those, feel free to. They should be at Calc Chat, so you should have the assistance you need. All right, we're ready for 5.7, natural log function. Let me get another sip of water or something here. By the way, I hadn't told this class, I told most of the others, but Monday, in the class that follows this one, the Cal 3 class, one of the students in the class said, he was the first one there. I said, oh, you're here early. He said, I've got nothing else to do. I tested positive. And he had very mild symptoms, so hopefully he's fine. And a lot of times, young folks like you may be fine. It'll be miserable, sort of like the flu or something like that, but not hospitalization type thing. No guarantee he didn't get worse in the last 2 days. I hope he'll be there today and still be fine. But he did have a sore throat. He did have drainage. He did have, a lot of the things. He thought it was just allergies. But when he started running a fever, they sent him to be tested. And sure enough, he came up positive. Well, that meant his roommate had to be quarantined as well. So far as the roommate hadn't shown any symptoms, but they're staying apart, and it was just an awkward situation. 2 weeks they're stuck in their apartment. He had seen his family about a week ago, and just depends on when his exposure happened. He's hoping he didn't give it to any of his family. I think not the weekend just before Monday, but a week before that is when he had seen them and his girlfriend, and he hoped he had picked it up sometime after that, so he wasn't unknowingly giving it to them. The point of saying all this, folks, is be careful, be vigilant, always, because this virus is still here. We haven't turned any corners on anything, no matter what the politicians say. It's still here. It's still dangerous. Okay? I think I'll share a little bit more. Our pastor's wife had it, and she had very mild symptoms. So that was all sounding good until I heard that one of our instructors' wife had it. The son brought it home from school. They should not have been sending kids back to school. Son brought it home. The son had either no or very mild symptoms. The mom is really, really, really sick. I mean, so our instructor is having to stay home. He's quarantined too, of course. His son's quarantined, and he was showing some symptoms, hadn't had a test results yet, so he's probably going to have it too. So, folks, be careful. Be very careful. All right, enough of that. So let's discard the annotations. How are we doing on time? Yeah, we got some time left. We go to 11:40. Okay, so we're through with 5.6. Let's move to 5.7. There it is. Okay, and we'll go from current slide. Come on. Yeah, we go. And we'll have to move my toolbar out of the way again, because everything screws up again when I go to a new slide. Okay, there we go. So we're still in chapter 5, integration. Now we're doing, if I can get it to advance, let me click on the screen, now get it to advance, 5.7, the natural logarithmic function and its integration. Okay, hey, we've already been fiddling around with that. Well, we're going to do it a little more detail. We'll use the log rule for integration to integrate a rational function. We came close to doing that in the last few examples, and then we'll also integrate some trigonometric functions. Okay, because some of those can be written as rational functions. So here's the log rule for integration. We've studied two differentiation rules for logarithms. Here was one. Derivative of log x is 1 over x. I hope you remember that. That produces the log rule for integration. Now here's another one. D by dx of log u, when u is a function of x, is 1 over u times the derivative of u, which is u prime over u. That produces the integration rule that the integral of 1 over u, now that's not written properly, it should have a du after it here, is log absolute value u plus c. Okay, those rules are summarized here. This time they did write it in right. If u is a differential function of x, no u's involved here, but the integral of 1 over x dx is log. Now why do we put absolute value bars there? Now I'm coughing. Because you can't take the log of a negative number. You can't take the log of 0 either, but obviously x can't be 0, okay? But x could be negative here. It can't, if it's negative here, you have to put absolute value bars around it. And this is an indefinite integral, so you have to do your plus c. But if you had 1 over u du, it comes out the same way, okay? So why do they say there's two different rules? It comes out the same way, okay? It's just you change your dummy variable. So there's no difference here, folks. It's the same. That was driving me nuts, saying, how are they going to do that? Now, but because du is u prime dx, what if you did have that, the integral of u prime du over u dx, then that's still log u plus c, okay? So basically, I mean, they're just sort of running in circles here, okay? It's still giving the same answer. So let's do the example 1. Okay, they've already given, well, they've started it for you, okay? First, pull the 2 out. There's no reason to keep it in there. Pull it out, and then this is just very simply what? 2 times, what's the integral of 1 over x dx? Surely you haven't forgotten that soon. Derivative of 1 over x dx is, wherever my cursor is, there it is. Oh, sometimes if I'm holding the pen too close to one pad, the other pad won't work. This is just log absolute value x plus c. So this will be 2 times the log of absolute value x plus c. Now, here's one thing, folks. Doesn't matter. C and 2c are both still constants. So this would be 2 log x plus c. Not the same c, but just the c. But here's sort of the good news. Because of the rule of logarithm, you can make this as log of x squared plus c. That's perfectly legal because whether x is positive or negative, when you square it, which you can do with the rule of logarithm, that's it. That's the simplest way to write this answer. Okay? Log of x squared plus c. Let's see how the book did it. They said that's 2 times the log absolute value of x plus c, and they may leave it there. Let's see. Nope. They write it like I did, log of x squared plus c. Okay, using the property of logarithms. That enables you to drop the absolute value bars. Because x squared cannot be negative, the absolute value notation is unnecessary in that final form. Good deal. So there was example 1. They are skipping example 2, 3, 4, and picking up with 5. So let's us do as much of those as we can. Let's start with example 2. if I can, well, I'm on the wrong thing. Okay, let's go to our whiteboard. And now I have to move this again. I thought, it's such a pain in the neck. Goodness gracious. Not that hard to move, but it's just sort of a pain. All right, I'm going to clear the drawing. No one needs that any longer, right? Okay, so here's example 2. There it is. Okay, example 2. Find the integral of 1 over 4x minus 1 dx. That's it, isn't it? Yeah. Now, folks, use all the tools in your belt now. That's why we got them. Looks like a u substitution. Let u equal, what's the most complicated part of that problem? That your variable's in the denominator, okay? Well, let's take that denominator and make that uu. 4x minus 1. Then, what's the next step? Du is equal to
4dx.
4dx. Excellent. Well, we don't have a 4dx, we just have a dx, so let's divide both sides by 4. Okay, so this evolves to the integral, and since this is an indefinite integral, let's take that 1/4 on the outside, because we don't need it inside the integral, and then see, these go away. Your dx is 1/4 du. Take the 1/4 outside. This will just be du over u, right? Because u was 1 minus 4x. And what would this be? 1/4 the natural log of u plus c. Now, and you really should put this as absolute values here. Now, I don't know that there's any advantage in writing this as log of u to the 1/4 power. You can't take the 4th root of a negative number either, so you would still need that plus c. Either one of those forms is fine. Oh, wait, no, wait. We need to go back and plug in whichever form you want to do, get it back to x's. Either 1/4 of the natural log of absolute value 4x minus 1 plus c, or if you wrote it in this form, which I don't really like that much, that would be the natural log of absolute value 4x minus 1 to the 1/4 power plus c. Okay, let's see how the book wrote it. They left it in the first form, 1/4 the log absolute value 4x minus 1 plus c. Good deal. All right, let's see if we can squeeze in example 3. I think I'll clear my screen here. Anyone need that a little bit longer? Yay or nay? Take that to mean no. So let's see, example 3. I'm going to have to pull my book over into my lap. It's heavy. Okay, find the area of the region bounded by the graph of y is equal to x over x squared plus 1. Okay, the x-axis okay, that's the x-axis, and the line y x equal 3. Okay. So basically, you really do need to draw the graph first. Okay. I just as soon not, but I'll suggest to you where this thing starts. When x equals 0, this will be 0 over 1, which is 0. Y is going to be 0. So you've got to be bounded by the x-axis, so your x value is going to start at 1 and go to 3. So basically this is going to be the area under here from 0 to 3, because it starts at 0, ends at 3, of x over x squared plus 1 dx. Okay? Now, no way to do this, I mean, you can pretend, but let's see. U substitution. Let u equal x squared plus 1. The part that's the most complicated part there. Then, someone tell me what my then is. Du is equal to?
2x dx.
Perfect. 2x dx. Okay? Now, we don't have a 2x dx. Oh, I left off. No, I got it there. We have an x dx. So let's divide both sides of this by 2. So we have an x dx, which is what we've got. So that means I'm going to pull out the 1/2 that went with the du here. I'm going to write my integral sign, but now I need to figure out what my limits are. When x is equal to 0, this will be 0 squared, which is 0, plus 1, u is equal to 1. When x is equal to 3, 3 squared is 9, plus 1 is 10, so u is going to 10. Okay? And then what do we have here? We got the 1/2 on the outside. The x dx is just du, and your denominator here is u. There's our good old log rule. That's 1/2 the log of u. But guess what? We can leave off the absolute value bars because everything, 1 and 10, are both positive, so you're not going negative here, and you're evaluating that from 1 to 10. So this is going to be 1/2 the log of 10 minus the log of 1 is 0. So that's it. 1/2 log 10 or log of square root of 10, however you want to write it. They left it as 1/2 log 10. Okay. Then they calculated to see what it was. Let me see if my phone is charged. I bet you it is. Yes, it is. Okay. Let me get my calculator if I can find it here. Now, the only reason I'm showing you this is that in case you do. I'm using a phone as a calculator. That's not going to work because I can't take a log function. You turn it sideways, you can get a log function, and I can't see it. It's lnx. Oh, there it is, right there. That's the ln right there. Okay, so what we're going to do on my phone, I have to press the argument first, the 10, then press the log key, and then divide that by 2, and that equals 1.151, and that's about what they said. Okay, and I think we have just run out of time. Okay, so let's close this down, and we will pick up next time with example 4. Did anyone have any questions on that? Example 3. Okay, we'll pick up at example 4. They don't have that on the PowerPoint, so we'll pick up starting with the whiteboard, and then after that we will continue in 5.7, not a very long section, so hopefully we will make progress there. Homework exercises here, I think you can do any of the odd ones. This is starting on page 362. Any of the odds 5 through 27. They're all at Calc Chat, 9's at Calc View. We haven't done a change of variable. I think that's coming later. Yeah. So, let me back up a moment here. Let me rephrase that. Let me say, do any of the odds 5 through 11. Do 5 through 11. I think that's going to be a better choice for you than 5 through 13, the other, because we're going to do a few more like the latter part. So any of the odds 5 through 11, they're all at Calc Chat, 9 still at Calc View. All right, any questions? Either what we were just doing, any questions whatsoever? And by the way, just looking ahead, we're going to probably skip over 5.8. I wish we had time to do it, but we don't. And we're definitely going to skip over 5.9, okay? If you need that, by all means go back and do it. So therefore, when we finish 5.7, which will be Monday, I will try to have your test ready for you by then. I think I may already have it ready, but I may have to do a PDF of it, because I used to do my test in WordPerfect, and if I don't have it in Word, if it's in WordPerfect, I'm going to have to take get it in PDF. Okay, so I'll try to have that ready for you Monday. Finally, I know y'all been anxious to get your first test. Any questions? And by the way, yes, Brandon, you have one? Okay, all right. By the way, I'll probably put the test in maybe 2 places. They do have this thing about assessment on, that'll be in week whatever. Is this, next week will be week 6, is that right? Week 6 is assessment. I may put the test there, but I'll also put it under Blackboard message. So whichever place you prefer to go get it, it'll be the same test. You only have to do it once, but I'll put it in both places in case some of you are used to doing one way and some used to doing another. I'll try to put it in both places. All right. Any other issues? Well, have a good weekend. Stay safe, people. I don't want any of you getting sick. So I've stopped sharing. And unless there are any other comments or other things, I'll go on and end the recording. Well, not the recording. I'll end the meeting. Any questions? Have a good, safe weekend. Looks like it's going to be sort of rainy now, so good opportunity to get some calculus done, including research papers, remember? All right, good deal. See you Monday, okay? Bye-bye.